Previously, we have studied the op-amp in different kinds of configuration. The first kind that we studied was the open loop configuration, which was the most simple example. But we had said that for the usefulness of an op-amp employs something called the feedback, where a portion of the output signal is fed back to the input of the op-amp. Now we have learned that there are two kinds of feedback. There is the negative feedback and there is the positive feedback. In positive feedback, the output signal is fed to the positive terminal. But in negative feedback, the output signal is fed to the negative terminal. And we do not discuss the positive feedback in this chapter because it has no practical applications for the things we are trying to do. So within the feedback and within the negative feedback, there is two kinds of configurations that we can use. The first kind of configuration is the inverting configuration, which we have discussed extensively in the previous videos. But there is also a non-inverting configuration, which we'll first start to study this time. So, what is composed of the non-inverting configuration? We can make a circuit that is very similar to what we have done previously in the past for the inverting configuration, which is small modifications to make this non-inverting configuration. So what we do now is we move the input signal to here, to this bottom positive terminal, and like before, we also have the feedback through the feedback resistor, but the difference now also is that we have the signal path on the negative terminal side is sent to the ground. So this is in figure in the textbook is 2.12. It's called the non-inverting configuration. So the simple observation is that we have moved the V in to this input node of the positive node. And then we have attached the ground to this signal path to the negative terminal. So you may be wondering, what is the reason for not studying the non-inverting configuration first? Why did we first study the inverting configuration? And the answer is that the non-inverting configuration is a little bit more complicated circuit to solve. Because previously, what we have done was that like before, we assumed in the ideal op-amp, the two voltages on the input terminals are equal. But unique to when we had studied the inverting configuration in the past, because one of the terminals was grounded, we were able to assume a virtual short circuit to the virtual ground, and that both terminals were 0 volts. But now we have lost access to this assumption. As a result, it makes the circuit solving a little bit more complicated, which is why we study the non-inverting configuration second. However, the basic principles of this op-amp, just like before, the basic principles, they all still hold. So let's review some things that apply from before. We just review it and implement it here. The first is the discussion on the differential signal. So what is the meaning by differential input signal? The meaning of the differential input signal is that this V in D is equal to V plus minus V minus. So that is one thing that remains the same. Another thing that is the same as before is the virtual short circuit assumption, called the virtual short. Just like before, we can still assume that V minus is equal to V plus, that this voltage is equal to this voltage. We can still make this assumption because this is the principle of the operation of the ideal op-amp. Just note that we have lost access to this virtual ground. But aside from that, this basic circuit solving principles, they still hold. Another thing is that in an ideal op-amp, we remember that in an ideal op-amp, the gain, the open loop gain is infinity. So the open loop gain is solely referring to if the op-amp was by itself. In which case, the differential input would say that, okay, V in D is equal to 0, because the infinite open loop gain ensures that this relationship holds. If that relationship holds, you just plug in and the result is that V in difference signal is 0. This is assuming it's an ideal op-amp, so that we can say V plus is equal to V minus voltage. So V plus, this voltage here, is equal to V minus. So let us solve for this circuit. How do we solve for this? The first thing we can try is to do this KCL. KCL, it says that let's call this current here is called this I1, and then this current here is called I2. Just like before, we assume that no current goes into the inputs for the op-amp, so therefore I1 is equal to I2. What is defined by I1? I1 is equal to this voltage minus this voltage divided by this resistor. So it is voltage of 0 minus V minus divided by R1. What is defined by I2? So I2 is this voltage minus this voltage divided by this resistance. So it is V minus minus V out divided by R2. Now, given the fact that V minus is equal to V plus, V in is equal to V plus, like here, so this is just the same voltage here. So given that, we just substitute this V in, and then we also know from the virtual short circuit approximation that V minus equals V plus. So we just, every time we see this V minus appearing, we just use this V in. So it's just 0 minus V in divided by R1 is equal to V in minus V out divided by R2. Okay. What we do now is we do this cross multiply. Negative R2 V in is equal to R1 multiply in parentheses V in minus V out. So now we can just like simplify for this and solve for V out divided by V in. That is the gain, closed loop gain. Okay, so let's just rewrite the left side, but the right side is doing some distribution. And so like we can like move the R into the move to here, and then that moves to here. So we can do like R1 V out is equal to R1 V in plus R2 V in. All I did was I moved this to here, and then I moved this to there. So like R1 V out is equal to V in R1 plus R2. So then we can say that the closed loop gain, which is defined as V out divided by V in, is equal to like R1 plus R2 divided by R1. So this is the gain closed loop gain equation for the non-inverting configuration for the ideal op-amp. Now one thing that is interesting is if I solved for V out, like we're solving for this, one thing that is very interesting is that V out is equal to V in multiplied by the gain. So it's like this or this. Actually, I will just write this. So what is interesting here is that you may notice that this closely resembles a like a voltage divider. So the observation we make is that a portion of V out is actually it's being fed back to the input, to the V in such a way that this signal path, it appears like in resemblance to the voltage division. So what is the behavior of this? So it's equivalent to a voltage divider, right? So the voltage divider circuit, or like resistor divider circuit, just different names on what you call it. The behavior then says that, well, you see, if as V in increases, then momentarily for a very small amount of time, the voltage difference here, known as VD, it is increases. However, because the differential input voltage increases with V out, then this will have to increase. So this the voltage difference momentarily increases, resulting in this value increase. But we have feedback going back to the input that forces to drive this voltage difference back to zero. And so it's a very closed loop kind of feeling to this. There is a name for this phenomenon, and it is called a degenerative feedback. And actually, I will write it down. So it's called degenerative feedback. Where the circuit drives V in D, voltage difference across the input terminals to the op amp, to 0. Yeah, so that is the meaning of this ideal op amp, and we have calculated the gain equation for this ideal op amp used in the non-inverting configuration.